Hi, this is Koiro and welcome to the second part of my MPS 801 video. And as we left this project last time, the fuses were still blowing and we didn't exactly know why. And this kind of puzzled me because it only was the primary fuse that was blowing, but if there was a dead short on one of the other windings, one of the other fuses should blow too. And we also established that there was some differences between the service manual that I found that was from 85, and I found a new one that's from 84. And this service manual actually brings some new light on several things actually. And this is the layout of the PCB that's stated in this manual, and as we can see here, it's the same revision number as we had in our video, and the fuses and the capacitors here are all placed the same way. And thankfully they also have a diagram that shows how these terrible connectors should be fitted with wires. So this will help out a great deal in our work. And this is the power supply that is stated here, and as we will see, there are some differences. The most noticeable difference is that there is no 7805 on this one. But the input voltages and the output voltages is the same as in the original, or not original, because this is 84 and the other one was 85, but our original manual that was stated as preliminary. And this is not stated preliminary, this is just marked as service manual. And as I said, the most noticeable difference is that this is not based on 7805, it's based on a series regulator with a transistor, a normal bipolar NPN transistor, and this is quite a common circuit. But as we see here, this is based on a 6.3 volt Zener diode that stands right on the base of this transistor here. And that means that we will not have 5 volt, but close to 5.5 volt output from this. Because you have the voltage drop of the Zener diode, that's 6.3, and you can draw from that the voltage drop on the basis emitter diode on this transistor, and that's typical 0.7 to 0.8 volts depending on how much current it goes in this circuit. So the 5 volt here will actually be closer to 5.5 volt output. 12 volt rail is almost identical. They have put an extra filter cap on the input marked in red here, and they also changed the filter cap on this side, and they've also put on an extra tap here on the schematic we saw last time, but this is not present on this schematic. The idea behind this is the full voltage, not regulated voltage, so this will be 20 volt and this will be somewhat higher, maybe 27, 28 volt or something. And I'm not sure why they have done this, and I didn't find it in the schematic either. And in our case, it's moot anyway, because this is not present in our printer. But what about the fuses? I said that I was puzzled that the 160 milliamp fuse on the input primary side was blowing, but not the other fuses. So I did some calculations and some thinking of this. First, I will go into a bit of blah blah on transformers. And this is an ideal transformer, and that's stated like the power you put into the transformer is equal to the power you take out of the transformer, but of course with different voltages and how much maximum current you can draw. And in our case, this is something along the line of this. We have 160 milliampere that runs through this maximum, and we have 1.6 amperes on both these lines. That gives out open voltage about 10 volt is the 5 volt rail, and this that gives open voltage of 26 volt is the 20 volt rail. So if we take into account that this is an idle transformer and we run 160 milliamps on this and 230 volt, we can actually calculate how much current there will go in each of this to make this fuse blow. And an idle transformer have an efficiency of 100%. But as we see here, this is the stated efficiency of a normal iron core transformer. And the output here, you more you draw of the transformer, you more efficient it will get. And this is of course different for every transformer, and a bigger transformer tends to be more effective than a small transformer. But this is just to give you a roughly idea, and they state that our transformer should have an efficiency in this range, something along the line from 80 to 85% efficiency. And that means that the rest of the power that goes in here will get lost in here in the form of heat. And in some cases also vibrations, because these transformers tend to vibrate somewhat. And this heat here will make a power draw on this fuse, but it will not make a power draw on this fuse because it's lost in the circuit before it comes to these two circuits. If we do some calculations of this to burn a slow, and this is a T fuse, they are time delayed fuses that can take a higher current for a short amount of time. We see that in an ideal transformer here, and if you run this with 1.16 amps, you will get a power draw of 37 watts. And now we are going to be a bit more technical. This is knowledge that is nice to have if you do some fault finding on all the equipment. And here we see the characteristics for a 160 milliampere T glass fuse. And it's stated that for a short time you actually can draw 1 ampere to this fuse. But as our fuse was not blowing straight away, I turned on the knob and it went maybe a half second and you can hear the fuse blow. And that means that you are somewhere in this area here for our fuse. And it's not much of a difference. You have 160 milliamps here and you have about maybe 200 milliamps here. And this looks a bit strange if you're not used to this kind of sketch paper, but this is a logarithmic scale. If we calculate this with 200 milliamps and get a delta for what we see here, you can see that we draw from about 37 to 46 watt. If we do some mathematics on this, then we say that the transformer in an idle world, if we do this on the 25 volt rail and we have a dead short on the other end and the fuse on the other side is blowing, we will have 1.84 amps, and that tends to blow the fuse. But if we take into account that this is a real world transformer, then we have to calculate in the efficiency and we only get 1.56 amperes. So that will actually not blow the fuse. So the idea behind having a 1.6 ampere fuse on the 20 volt rail is not a very good one, because this fuse will actually not even blow with a dead short on the 12 volt rail. Then it's the primary fuse that will blow. So this fuse is almost impossible to blow if you short the circuit as it is. And that means that if you make a dead short, it will be 170 milliamps on the other end in an ideal transformer. So that means that the fuse will not be blown in a real world example. But what about the 5 volt rail? We know that with 220 volt with a current 160 amps on the primary side and the efficiency of 85, and if all the power is drawn on the 5 volt rail, then is no power on the 20 volt rail, then we will have 4.6 amps on an ideal transformer, but with the 85% efficiency we will have about 3.9 amps. Does this mean that the fuse on the 5 volt rail on the PCB should have tripped? And yeah, it does. It should have tripped, and if we compare the two fuses here, you will see that you do actually have a bit of different characteristics on this 1.6 ampere fuse. You do have a more of a bend here in the curve. That means that on this part of the curve it will take a bit more power to trip this fuse than it normally would. But anyway, there is a dependency here. You have 3.9, it will be about here, the current draw on this. And as we see here, this means that the fuse should have tripped anyway, because we are in somewhere inside this red area here and probably along the lines of this. This is what makes me puzzled and makes me think that there is something I've missed in this circuit. So even with a time delay fuse, this should have tripped. There is no way that this fuse should have survived the kick that was kicking in with a dead short on the 5 volt rail. So this got me thinking that maybe the Sherlock Holmes way of deduction is a dead end here. I need more information because there is something that's not right about this. Why did not the secondary fuses blow? There is something I'm missing here. And I went back to the shed and I picked out the fuses and measured them. They was okay, but then I found this. Okay, but this one has been changed. The fuse on the 5 volt rail was actually not 1.6 amp fuse. And this is of course something that we should have spotted right away, but we didn't. So the fuse here is F, that's a fuse with a different characteristic than the T fuses. And it's also a 2 amp fuse, not a 1.6 amp. Maybe this is a factory thing, maybe it's not. But anyway, we did all the calculations, we did all the thinking, and I did the fault finding and preparation for finding more faults based on bad data. And F fuses, quick blow fuses, they say they're quick blowing, but that means that they don't have the time delay that's actually stated in the other fuses. But even though, if you take the 2 amp fuse here, you see that this is the characteristic of this fuse, and down here you have the 4 amps that will have gone into our circuit, and this is the 10 amps that is the bottom of the same characteristic and time frame I had on the other curve. And that means that this fuse actually would survive because the current draw that we have is in this window here. So when we dug deeper into this, we saw that the theory behind this and my thinking was, yeah, dead spot on from the start, but it was based on one false pretense, and that was the original 1.6 amp fuse and not a 2 ampere fuse with a different characteristic. So then it's back to the shed for some quick measurements. From our calculations, we already know that the fault probably lies on a component on the 5 volt rail, because if there was a dead short on the 20 volt rail, it will not be able to trip the primary fuse so fast as happened in this case. So we have to measure the bridge rectifiers, and bridge rectifiers is just array of diodes and they can fail short or open. We also have to measure into the circuits to check for dead shorts. So in short, we just measure out the VCC points here, and if there is a short, every one of these will be short, and we have the 20 volt here and here as a test point that we can test out. So that will be our next task. So I will go out into the shed and do some measurements about this now. But at least now we have a very good idea of what lies in front of us. Yeah, a bridge rectifier is approximately, or not approximately, it's always something like this. And you have in here, you have the AC voltage. So this is AC and this is AC, and out here when you have a leading plus here, so you have this one giving out 0.7 volt less, so it will go out like here. So this will be the plus and this will be the minus. And the theory behind this is that this diode here will lead when you have a positive pulse. This will go out plus here. And when you have the negative lead here, it will take this diode and give out the negative pulse here, because this will be the opposite direction. And you have the same here. If you think this is plus, you will have this one forwarding this to this one, and if you have the negative here, it will forward this to this one. So this is always like a bridge rectifier will look. So I will measure out these bridge rectifiers that we have down here, and they are stapled on top here. I don't know if you can see this, but you have the plus here, you have the minus here, and you have the two AC lines here. So it's almost exactly like we have here. And that means if I put this one on the ground here, I should not get anything against the other diodes, because they won't lead. So if I get anything here, it's a capacitor or something. But if I put the positive lead here on the GND, the ground, I should get one diode, and that I got like so both ways. And the same if I put the minus on this side, yeah, one this way and one this way. So at least this one is totally fine, and I will do the same with the other one. A bit hasty. If I put the plus here, and yeah, this one is okay, and this one is okay, and if I put the minus here, I should get one there and one there. So both the bridge rectifiers are okay. And if I measure just into the circuit, if I put this on, yeah, maybe 2 kilo ohms, and I measure just inwards from the power in, I'm not getting a short. So that means that the short actually are behind the bridge rectifiers. So the next thing I can measure as a source of the fault is that I can measure the transistors that actually stands here on the side of this metal bar here. We saw them last time. They are fastened here with insulators as cooling here. And the next thing that we can measure out is the transistors that stand as a series voltage regulator. And we have one coming in here, and we have one coming in here. They is connected with these leads here, this one and this one. And if we identify that at once, what's what in this, you actually here on this circuit have the big capacitor. This one 50 volt, and it's on this down here. So this is the 12 volt, and this up here is the 5 volt regulator. And if we measure this one first, I'm not sure how what is what here, but that we can find out. We have the input here that goes like so, and this is, you know, the minus goes out here, and this is a capacitor, and it's not short circuited. And we can measure out this transistor here, and this is the transistor that goes into this circuit. And you have here, this is the plus, it goes like so. So the plus on this should be the collector, so the collector is in the middle. And you have the Zener diode stands here, so this will be the base. So the base to collector, it's a bit low, but it seems okay. And the base to the emitter also seems okay. And there is no short circuit in this. And we can measure the other transistor too. And this is the one down here, and this is the 12 volt. And you have this one, this is the output for the 12 volt. And the output is the emitter, like so. And this is the input, it's the collector in the middle. And that seems okay. And this is the base. And the base on this one is connected to a diode, and this diode is the one that stands over here. So this is the base and this is the connector, and that seems okay, and the base, that seems okay. Both these transistors should be NPN transistors, and when you measure them out you actually can look into the symbol here to see what you expect to find, because this is a diode. So over here, when you measure from base, collector and emitter down here, when you measure over here, this should be approximately 0.4 to 0.8 volt, and this one actually is the same. It's not stated in the schematic or anything, but this should measure just the same as this one down here. So when you measure on an NPN transistor and measure with the positive in the base and the negative down here, you should get about something like this both ways. And both these transistors in this circuit is NPN transistors. So then it's something further down the line here that's shorted. You can of course lift out this EEPROM. This is a normal 2732. See if something has changed. No, we're getting the same, so we can conclude that this EEPROM is okay. This microprocessor here is an M5L8039. I'm pretty sure that this is a clone of Intel 8039 microcontroller. What we have established so far is that if I measure from the ground rail, take this point for instance, and measure to this test point for 5 volt, it's about 0 ohms resistance. If I take and turn the multimeter the other way just to make sure that it's no capacitor that fools us, you will see that it is the same. So that means somewhere here there are a short for the 5 volt, and of course we can take the connectors and disconnect everything that we can disconnect to make sure that the short is not outside the board. I mentioned before how much I dislike this kind of connector. It's so easy to make mistakes and have the fault in the connector. And the rest of the leads, that's for the transistors that we have here for the regulator supply, and they are soldered direct to the board. So now there should be no additional contacts or circuits that should affect the measurements. And I put again this lead here to ground and measure on this test point, and it's about 0. That means that the faults still are on this board, and we can take and measure out the other active components as well. This is a transistor and is marked where the base are. Yeah, this way it looks good. The base is to collector and base to emitter seems a bit low, but there might be a resistor. And we do have the same on this one, and no short. So these measure out okay, and I have one more here, a small driver transistor. Sorry, but the lightning blocks out the display on the meter, but I'm just here continuing to measure out all the active components, and it's all bipolar components that should have a diode forwarding of about 0.6 volt. Yeah, I've been changing batteries in the meter. My Metix is very reliable, but when it starts to get low on batteries, the ohm function doesn't work properly. So now you can see the battery is okay, and it's measuring about 0.2 ohms at the end of the leads. And if I measure here against the 5 volt rail, I get about the same. So somewhere along here. And it's probably one of these ICs that actually is short circuit. So I think it can of course be other components as well, but none of the resistors looks burned, and none of the capacitors that's here. We have, if they are standing straight across the 5-volt line, I of course should measure a short circuit on the capacitors as well as I do on everything else on this line, so that's why I can say that. So I will just take and desolder these ICs, and we take it from there. This PCB is for all purposes when it comes to desoldering single-sided. And back in the day when all PCB was single-sided, this desoldering really was a walk in the park. On this PCB, the soldering is done by lead solder, so it's melting quite easy, and it also is sucked quite easily into the solder wick. But we do have some stubborn ones, so we do have to take another turn on some of the points where the solder has not completely been sucked up. But now it's just to pry out the chip, and it loosens quite easy. And I can try to measure again, just into the 5-volt rail, and it's still the same. Yeah, I will just continue this desoldering mission.
Another one bites the dust. Another one bites the dust.
And we again measures over the 5-volt rail and finds that there is no change. So the next I will do is to try to desolder the capacitors, and I should have done that from the start, but somehow I thought in my head that the power supply was decoupled from the circuit now, but of course it is not. So that's what we will be doing now. We will desolder all the electrolytic capacitors in the power supplies. So now we actually can measure again to make sure that it was none of the capacitors that was giving us havoc. But it actually seems like it was. And we just use a ohm meter and ohm the capacitors. There is no reason to go with a capacitance meter or something. This was a shorted capacitor. And when we find it, it will have 0 ohms resistant both ways. And here we actually have found the fault. This capacitor here, it's 220 microfarad and 6.3 volt. It has a ohms resistance of 0 about each way. And I will measure the last one. Yeah, so that means we actually found the fault, and we did the unnecessary desoldering of the chips. That's a lesson learned for another time. I will actually put these just back in, and I will put on a new capacitor and just put everything back in place. Yeah, luckily we didn't manage to do much damage, and just desoldered the 2 ICs, the processor and one logic chip, before we saw the errors and desoldered the capacitors. So now we just solder everything back together and replace the faulty capacitor. I have to check out the two other small capacitors because I don't remember where they should sit, so I have to mark them out by the schematics. But this actually is the one that was rotten, and if I now measure into this circuit like so, test point and ground, it looks good. So I will just go and get a new one of these, and I will solder in the rest of the capacitors too, and I think we actually will give this a test. And here is our new capacitor. It's a 16 volt 220 micro, not a 6.3 as the last one. This is the two old that we are reusing, and this is 47 micro. 47 micro is C4 according to the schematic, and that's this one. And I do have the last one here, that's 50 volt 1 microfarad, and that's C21, and this is the one up here, and it has the positive side this way. I will just solder in these ones. And then it was only this one left, and it's the C3, stands here. And this should have the plus leads up like so. And then it's getting all these connections back in. We do also have to connect the power supply and connect the leads, and we have to fit the plug, and we have to fit the switch on the side. And the cable for the power supply was running underneath the printer mechanism. Before we put it all together, we have to install the right size fuses in all the positions. And that means I have to go inside and get some new ones. Yeah, I'm back with fuses, and this is from a different assortment box than last time, but this is 1.6 amperes, and it goes like so. And this one is 0.16 ampere. It goes like that, and I don't think I need any more than this to give this a test. It should light up, and it should spin some wheels or something, even though I don't put this fully on. Yeah, it actually started to print, and that is probably because this might be in test mode. I have to find the backplate to actually see. Yes, it's in test mode. We actually get to verify more than we wanted, so we just power it on again. Yeah, and it runs through the home sensor to see where it should be, and we already established that it tries to print something. So until we get a printer ribbon, or is able to fake some printer ribbon stuff, that actually is it for the episode about this this printer. I think we can call this a success, and it was a long and winding road to a good result, but we actually managed to fix it in the end. And hope you enjoyed the contents, and please hit subscribe if you want to be notified when we post new videos. Thanks for watching, and see you in the next one.